Okay, guys. Is this loud enough? Okay, cool. So, okay, first, thank you for attending for today's lecture. So, in today, we are going to talk about the one real algorithm idea, which is called brute force. And let me mention, we left something about the empirical evaluation last week. I will pick up that one after we've gone through about today's lecture for lecture 3. So the reason is I will also spend some time in today's lecture to go through the assignment. And within assignment, it's directly with the empirical evaluation. So that's why I put one after today's lecture. So that's the reason. So now let's get started. Okay, so brute force is actually, we try to get some idea. So now let's get the idea first. So we're talking about algorithms. So when we're talking algorithms, it's really how to show you get the idea to design efficient algorithms. So it's not a specific algorithm. It's not a specific algorithm like a bubble sort or something. The thing is behind the bubble sort. The thing is, okay, why bubble sort works? What is the strategy idea used to develop the bubble sort algorithm to solve the sorting problem? So that is the whole story. So we focus on algorithm. The algorithm we cover are examples of some ideas. Some of those algorithm ideas. Brute force is one of them. So in today, we're talking about brute force. So we get sorting, computational geometry, and exhaustive search, and a graph search. And all this is we get some algorithms using the brute force idea. So that's what we do. Okay, now we get the idea is something like this. So for sorting, we get a selection sort and a bubble sort. And when we saw the sorting, and if you have already gone through for assignment 1, you notice within assignment 1, we get something like sorted double linked list. So we get a term, a common term, sorted. So which means you need to use some of the sorting algorithm, either bubble sort if you like, either you can use the selection sort, that's fine. So you need to use different sorting algorithm to do implementation. I will discuss a bit more that related with assignment later. But within here, let's focus on, we're talking sort, we're talking about the graph search, and we're talking about the computational geometry. So all that is linked to some of the problem, and we need to solve. To solve it, we get some ideas, like a bubble sort, or we get a selection sort. Either selection or bubble sort, they're actually coming from brute force. So I want to get this one first, and then we'll continue. Okay, now we continue. So we get brute force. So what actually the brute force? Now, possibly you get a definition yourself already. But to make something systematic, we need to have one kind of definition. So the brute force is something like that. It's actually quite a straightforward approach to solve the problem. Based on what? Based on the problem statement or the problem definition. Some concept within the problem, we just borrow that idea and solve it. So one direct example is our old friend, it's a to the power of n. So we use this one example from the very beginning. So the way we do the implementation is we calculate a to the power of n. The meaning for this term is they multiply a for n times. So that's the meaning for a to the power of n. So what we do is we just code it in that way. We implement one algorithm to multiply a n times, and then we get it. So that's the very straightforward definition about what is a to the power of n. So we do it. So it is something we call the brute force. So that's it. If this one is good enough to understand, the second one is a bit difficult. So something like that. Now we do searching. Searching for a k of a given value in unsorted order. And you may think, this one is related with the brute force. Let me give you one example you will understand. So why this statement says something like the searching strategy after this is the brute force. The searching for a k of a given value in an unsorted list. Because it is unsorted, if you want to find whether that k is in there or not, you will have to do the comparison with each one of them, right? So in that case, which means you really go through all those possible positions for that value, and then find the one matching the value you are looking for. So it is brute force. Okay, now we continue. So we get sorting. So now the idea is we got sorting. We try to sort something using the idea of brute force. Now let's get the idea. So we get the telephone books. The telephone books normally you get, possibly you do not use it. I'm a bit old, so I use it well. So something like that. You get a telephone book with all those numbers, but sometimes we put the people's name in alphabetical order, and so you can pick up the right one's phone number quickly. So that's the one sorted by surnames. And you can also check the highest in the class from the tallest to the shortest. So that's all right. Okay, now when we get sorting like this, and you may think, okay, how do we sort it? We can manually do one by one. It's one solution. It's the brute force solution. That's what we're going to talk. But to do that, if you really think, okay, why I need to do that? Why should I sort? If the telephone book is not difficult enough, let me give you one example. So when we work at a SIG, so for example, we get your query, you go to SIG website, you put one query set, I want to find all those job attachments with advanced programmer or programmer. Do you know how many of those job ads are there? Roughly you get 500,000 job ads, active job ads in there. And if I want to do search, I do not sort, I will do a brute force comparison and search. You find one query program against 500,000 of the job ads to compare whether that job ads have the job title include program. You need to spend roughly 7 days or even more to do that. Even you compare one in 1 second. So it is something like that. You go to job seeker. You go to SIG website and you put one query program and hit the button and you get a message to say, oh, wait, hold on. I will give you the relevant document within 7 days. I'm pretty sure you will not be happy. So that's why we need to sort. After we sort, we can improve the efficiency for searching. So sorting is something like we need to build up the sorting first, and then on it, we can build efficient searching algorithms or data structures. Okay, now when we link to data structure, today we have one example. So you get one idea. The idea can be implemented with the different data structures, like the graph. We get a matrix representation, or we get a linked list. And when you use a different data structure to implement one algorithm, you will get a different efficiency. So that's why we need a data structure. For data compression, it's actually compresses the data. I just put in there one example. We do not talk about data structure in this course. Now we'll continue. Okay, for sorting actually have been researched for years, for decades, for quite a long time. So it's heavy study. And within here, what we try to get is we try to get a definition about what is sorting, and then we're talking about those ideas based on brute force strategy. So the sorting problem, the mathematical definition will be something like that. So we get a set of the elements. So it's a sequence of the elements, and we try to rearrange them according to some order criteria. So that's what we do. Now, we get that, we start to do our selection sort. Okay, now selection sort is something like you will brute force go through each of the possible solution, and then you get it. So the meaning will be something like that. We first get the whole list of the values. We start from the very beginning, and then we find the smallest one by doing one scan across all those values, and swap with the first element. And then we do the second scan by doing something like we check it from the beginning, the second element, and scan the rest, and find the smallest, and then swap again. It's something like that. It's something like we are doing ordering. So instead of ordering across all those elements, we do one element sorting at the moment. We always find the smallest value in the current set of the values. we find the smallest one, take it out, put it in the first position. And then for the rest of them, do a second scan, find the smallest one in the second scan, and the rest of the elements, take it out, put it in the second position. We'll do that for each one of them. So that is basically what we call, this one is called a selection sort. So it is easy. Okay, now what we try to get is, after we get this idea, we will go through some examples and then analyze its efficiency. That's what we do, right? And then we will do comparison with other sorting algorithms to see why for brute force strategy they get different algorithms, and for the comparison in terms of efficiency, they're roughly the same. Now let's get some details. Okay, now we here get one of the vectors. We call, you can get just 12 values in a set. Now we want to do selection sort. So we will scan the 12 values, and we'll find the smallest one. So what we do is we need to do a comparison. Basically, we compare this one with the rest of those 11. You find the smallest value and point where it is. So it is 1. So after we get the smallest value in the current set, and then we put this one to the first position, and scan the rest, and find the smallest value in there again, and take 3 out, put it in the second position, and then we scan the rest. 5, put it in the third position, scan the rest, get the 6 is the smallest, take it out to the fourth, and do this one again, until finally, okay, we get 25 is the last one, we don't need to compare, we put at the end of the list, so we get it. So you may notice that there's something like this one is recording the number of comparison you need to do the selection sort. Okay, now, after we get this one, that's the one we said the big CN function. Remember? Okay, now, if we think this one is not that bad, the reason is the input size for this example is, who can answer the question? Raise your hand, please. Could you count how many numbers in there? Okay, cool. But 11 is good to try 1 chocolate. Cool. Okay, now from here, what we can say is the input size actually dominant how many number of the comparisons you need to do. Okay, second question. So when we count the kind of the comparison, we actually given one of the concept. What this one is called is something. Who can answer the question? So we get input size. We call that 12, and within here we call okay. This comparison is the number of the runs for some kind of operation. What do we call that operation? Okay. Yes, basic operation. So factorial is different answers. Factorial basically means that's the equivalent classes. So you get efficiency, several different equivalent classes. I will try. Great. Sorry. Okay, now we continue. We move on. Now, I get several answers. Sorry, I get several questions actually. So here we get the pseudocode. Now, let me try to link the idea together. We first give a definition about what actually is the selection sort, 1, 2, 3, 4 bulletin points. That's the steps. And then we go through the animation to show you how do we do the selection sort based on the 12 input examples. And now here we get a pseudocode. The pseudocode is something like a more higher level to show what actually is the selection sort. And I'm pretty sure we know what it is. What I try to get your attention to is something like this. Could you please tell me what is the input size for this selection sort based on this pseudocode? Oh my God, it is n. And then what is the basic operation? I heard several answers. Can you answer and raise your hand and explain why do you see that? Okay, so why you see comparison? Say it again. basically write? Can you be more specific? Because a basic operation means it takes more time to write. That's okay. But the basic operation is you get several operations. You get an assignment here, you get a comparison here. I think you mean comparison within here. So the main reason to pick this comparison and the basic operation is because that's the operation you run for the... Correct. So the most frequent occupied or executed operation, we call that basic operation. Excellent. Sorry. Yeah, so now that's the basic operation. And the reason for here is either you see comparison, you see assignment, you see addition, even for the loop around here, or correct. Because within here, we do not distinguish too much about which one actually takes more time for a single basic operation. We try to find, okay, what is the one dominant or most frequently executed operation within this pseudocode? I think you get it. Now, I get one more question. Do you still remember what is CN? And the question is, can you give what is CN for this pseudocode for selection sort? Okay, no people? 2 chocolate. Cool, get one. Say it again. Can you explain more? Yeah. Anything more? Do you have more to add? So your explanation is half. Do you have more answer to add for your answer? Okay, can you?
Can it be either 1 or n? Depending on the worst or the best case.
Okay.
If you find it in the first calculation, then it's the best case, so it's 1. If you don't find it in the only list, then it's n.
Okay. Both of you give half of the answer, so how about you share? I will try, sorry. Okay, now I want to point to something like this. We get one for loop, the second loop. I remember last lecture, one of the super genius guy sitting around there gave a term to say that's the inner loop, outer loop, and those 2 loops control together for the summation across the basic operation. So we get something very fancy, remember? 2 very big summation together to calculate the number of operations we need to run. Anyone can try how do we get those 2 summations together? How do we get it? Okay, I'll take 2 for myself. Okay, now let me point you. That's the one. So we get 2 for loop statement. It's nested. It's nested for loop statement, 4. And that's why we calculate how many of the basic operations that we need to run. Let me point something more closely. So this 4 is from I equal to 0 to n minus 2. N minus 2 because to the second last element, because if we get the last one, we do not need to compare. So we only go to the second and last one. And for each of the one, we first assign this value, this count index indicate the mean value, the minimum value within the count set, and then we go through from the rest to the end and to find whether that one is smaller than the count mean value, and then if it is, and we record the count mean value as j, and then we do that. So now that is 2 nested for loop statement. 2 nested for loop statement, if we translate it into the number of basic operations we need to run to say n, basically, we get 2 nested summations. Now, I want to put you here about attention to those indexes here. Sorry. So indexes is for this one is, the inner one is I equal to 0 to n minus 2. I equal to 0, n minus 2. So the index we put within the summation is actually the index we used in the for loop statement. We check the second one, we start from j equal to a plus 1 to n minus 1. perfectly match. And for each of those loop, and we do one basic operation, is a comparison, assign, or addition. And here we only put 1. And you may think, okay, right now, you get 3 operations, why just 1? We put 1 here, or we put 1 plus 1 plus 1, we get 3. 1 or 3 does not matter. Remember, when we analyze for the efficiency, we try to omit the coefficient. So 1 or 3 does not matter. So we just put 1 here. So that's why any answer around here is correct. Now we revisit what actually is input side, the basic operation, and the CN. Now let's look at something in details. Okay, now I will copy the equation here. Now I need to simplify this summation into something. And do you still remember when we simplify this equation to here, we use the 1 rule? Do you still remember? If you remember what is the rule and we used it in here, can you raise your hand, please? We discussed the last Thursday. Feel free to check your note if you want. Yeah.
You get rid of the 1 and the I because technically they're constants.
Perfect. Perfect try. But I here is part of this index, so it is not a constant, but good try. Yeah.
Can you just replace the I with n-2?
Okay, that's a good try. Yes. Okay, cool. We get 2 bit, basically, right? Can you raise your hand, please? I cannot. I'll do my best. Okay. Any people want to try? I really want to get you to try how do you actually do the calculation. It does not matter if you get it wrong. Okay, cool. Good answer. Oh, you get a bigger one. Okay. If no more try, okay, let me see. Something like that. So we first explain we got the inner one. So what we do is we actually get the top end index, n minus 1, minus j, and a plus 1. So the final answer will be n minus 1 minus I. And when we get this stage, we will get 1, only 1 is a constant, so we can remove it. And n is actually the one it will be added for n minus 2 times. So we get this one out. And then will be another simplification rule for rule 2 within last week's lecture. We get 1. The final answer is this. Okay, now let me explain. If you really don't understand how do we get this one, it does not matter. Because it's not expected to, you can analyze that efficiency in a new algorithm. As long as you can understand what we covered last week, it's fine. But my job here is to try to repeat all those important messages again and again to make sure you get better and better understanding. So now if you don't understand this one, that's fine. And if you want to get a detailed answer, come to me, I can show you. But you finally need to answer something, finally you need to understand something is like this. So the Cn for the selection sort is actually n minus 1 multiplied n over 2. So that's it. If we put this one further, this one should be belongs to O n square. I hope you still remember what it belong to. What actually is O n square. Say it again. Yes, correct. I have to give you one. Yeah, so On here actually is the equivalent class. Sorry. In terms of efficiency, so because within here we thought we get n squared is actually the dominant term, so we discuss the rest. So we get On squared. So that's it. Okay, now we'll get some of the question here. Sorry. It's not a question really, it's actually the detailed analysis. So from here we can say we need to run around an n squared over 2 comparisons for a selection sort, and at the most n minus 1 exchange. There are 2 things, comparison and exchange. That is actually 2 actions. For exchange, normally what you need to do is you need to do a swap something. The worst case you do is actually you have to do a read and write from the tape. That's the worst case. But within here, what I want to point to is for different operations, they will actually affect the efficiency for your algorithm. We quickly link to our assignment. There are several actions that require you to analysis. Addition, deletion, or removal, you get search. Different actions. For different actions, they will definitely affect the efficiency. So, in your assignment, the expectation is you can do analysis for each one of them, or the combination of them, or a mix of them. I will talk a little bit more later. But from here, what we want to introduce another idea is, even for one sorting algorithm, they have their own advantage and disadvantage. It is pretty for sure. That's why you need to pay attention to. I cannot show you all those sorting algorithms, but what I can show you is what is the part you need to pay attention. That is the part. Okay, now we'll go to the next one. Next one is the running time is insensitive to the to the input. So why we say this algorithm is insensitive to the input? That means, okay, the result lead from there is we get the best, average, or worst case are essentially the same. A big question mark. Why? If you get answer, raise your hand, please.
Since it has to solve all the way through the list each time, it can't get any better than that. It has to go all the way through to the end to find and play first, and then it has to always go right to the end. So
100% correct. That's the reason. Because remember, we do comparison. Thank you. So remember, we do the comparison. The comparison is the selection sort. Every time you will scan the whole list, find the smallest, take it out. Then scan the rest and take it out for the smallest. There's nothing you can escape. You have to do all the comparisons, which means the number of the comparisons you need to do is always around n squared over 2. That's it. So either best case, worst case, or average case, all the same. So it is insensitive to the input. Now we continue. Okay, so now we get, even this one, n squared is pretty high. It's really pretty high. But why we do that? Because n squared, if you only do 12, the size is 12, it's okay. But if the input is millions, n squared is a huge number, we can't do that. So why we still need it? Because for some of the operation actually here is better. For example, when write is much more expensive than read, selection sort may be better because the selection sort does not need to write too much of the information. And another one is for small arrays, it's relatively quick. So it's kind of efficient in terms of those when n is small. So when you are not dealing with the search engines for millions of those websites, possibly you can use it. So selection sort is easy to implement. It's just a bit high in terms of cost. Okay, now we get another idea. So after we do the selection sort, so whatever it is, the selection sort or other sorting algorithms, we want to find the sort. What kind of the sorting result we can get from that sorting algorithm? So let me specify. The question is, you sort something, but that does not mean all the sorting algorithm, given the same input, they will give the same order, does not necessarily be the case. You may think, okay, why? Because we get something duplicate. That's the term. We get a duplicated case within the input. It's possible. How do those sorting algorithms deal with those duplicated words? It's one thing we need to check. It's what we call the stability of the sorting algorithm. Okay, now what we mean is something like that. We get a two list, before sort and after sort, and we get the value actually is 1 Adams, this one is Smith, and when we after sort, before we sort we found Adams actually in front of Smith, after we sort we still found Adams in front of Smith, so in that case we call okay. Now this sorting, it is stable. Because for the duplicated keywords, they maintain the same order when the original list. Okay, now, question. Is the selection sort a stable algorithm? Given the following numbers, can you take out a phone and scan this QR code and put in the answer? Please. You will find there are several answers. Yes, no, and the third one. And think about it, and click your answer. So all the collections of data from here is anonymous, so don't worry. Come on, we've got more than 30 students here. Please. Okay, now, if you really want, you can grab a pen and a paper and draw something if you really want. Use the selection sort to sort the input array is actually 4 values to see whether you can get the same order. So pay attention to the first 5 and the second 5. Right now, the first 5 is here, the second 5 is here. So after you sort, can you still maintain the first 5 is before the second 5 for selection sort? Now let's check about, wow, it's pretty equal. Okay, the biggest one is actually depends on how we implement the comparison. Strict or not, and we get yes or no, 35 for yes, and a no for 25. Okay, now, could we answer no? Raise your hand and give an explanation about why you answer no. Please.
Comparison will never be true. And you won't be able to find when you're doing comparison, it won't. Use the brute force.
Yes, it is the brute force for selection.
The comparison will never be true, but it does less than.
Yep.
It's not less than or equal to, it's just less than, so it won't be true, so it won't have the sign when you value.
Okay, I think I got you. So your point is when we do the selection, you only compare it's equal, it's less, and if it is less, you do the swap. Yeah, otherwise there's left there. Basically correct, but can you add more details, please?
Well, the first one you've got is already in order, so it stays at the beginning of the list.
Okay, cool. So I will add more later. Thank you. Okay, now we get the explanation for no. Who answer yes can raise their hand and explain why you answer yes.
Because selection sorting will go through every element of the group, of the set. So the original sequence, even those like 5 and 5, they will maintain the original order after it has been sorted. Because it takes the first 5 out and then the second 5. So the original order was maintained after the sort.
Okay, roughly fine, but I will add more details later. So who answered it depends? Please, raise a hand, please. So we can get more discussion from here. No.
I was thinking if there's a strict set of rules on whether it takes the first, like if there are multiple keys that are the same, if it always takes the first, then we've got a strict set of rules that we would definitely know how the algorithm is going to organize. But if we don't have that strict set of rules, then you would never know what would necessarily be.
So you mean the strict is strictly defined? How do you compare this value with the smallest value at the moment? It is actually less than or equal to or something like that? Is that your point?
Yeah, I guess so, yeah.
Okay, cool. Basically right. Okay, now what I want to show you here is that let's go back. So it's basically this operation. So that's the comparison. The comparison between the current smallest value with the counter value is to see whether the counter value is smaller than this one. If it is small, and you record it. And finally, you actually bring that one to the front. So that's what we do. That's okay. But the correct answer here actually is, for selection sort, it is not stable. Why? I will just give you the illustration about how do we actually sort it. So the way is we do something like that. We do 5A, we start from the first one, and scan the rest to find the smallest one. We get 2 is the smallest. We put 2 in the front and put 5A in here. That's what we did, right? And then we start from the second, scan the rest, find 3, put 3 here, and 5B here. And then we go to 5B, we compare 5B with 5A, and we'll find 5B is not smaller than 5A. So actually what we did is we will maintain the same order, and then we will get 2, 3, 5B, 5A. So they swap A and B. Now come to your answer. If we do not get a very strict comparison, small or less than, we do small, less than, or equal to, you may get a chance to swap A and B. From here it seems it is stable, but I tell you the answer is not. You can try more duplicate values, you will get a more complicated illustration. So the correct answer is not stable. But to check when is the condition you define, is it strict or not, is a very wise decision you check. And for you give right answer and wrong answer, it does not matter. So what we try to get is you get a deeper understanding about why you think one algorithm is stable or is not stable. Okay, now we continue. Okay. Now we come to another sorting algorithm called bubble sort. So the bubble sort is we compare the adjacency atoms in a list and then exchange them if they are out of order. So what does that mean? That means something like this. So first, the bubble sort is a very classical algorithm. So what do they do actually is it initially designed for tapes. The tapes actually is for tape disk is for something like, it's not like the flash drive you get right now. It's not like the hard drive. It's a tape. It's a tape actually, every time you want to access something, you have to rotate. You rotate the right position, you access the value. So in that case, to rotate the tape forward or backward will take more time. So the bubble sort is designed for tape disk. And right now with random access memory, like we get RAM, we do not use it basically. But why we put it in here is because we get the inset for things for this algorithm. Now, let me get your point. The point is, let's back to the 1970s and 1980s. At that stage, there's no random access memory or something like that. They're just tape disks. If you will still need to do some sorting functions, we need to design some very efficient, quick algorithms. At that stage, bubble sort is quite efficient. It's quite an advanced technique. So the point here is actually, when you're facing a problem, you need to start from the problem to think, how do you design a new algorithm to make that problem solved in a more efficient way? That's the idea we can borrow from here. So this idea is they always compare to adjacent items, and if they are out of order, swap them. So which means you do not need to roll your tape forward or backward. So you can make it very quick. You just do several rounds of pass. The code is very simple. Now let's look at more details. The detailed thing will be something like that. So when we do the comparison, so we compare each of the adjacent pairs of the atoms and swap them if they are out of order. So the directly result we get from the first pass will be the largest value we'll push to the end. And then when we repeat the previous step, what we did is we can start from the first to the second last element because, to the second last element because the largest element have been put to the end, so we don't need to go to the end. So every time we do this one repeat, from the second to the from first to the second last, and from the first to the third last. So you do some kind of bubble sort like this. So you do a number of those sorts. The number of sort equal to the size of your input minus 1. That's what we did. So now we look at what we do. So we come to our old friend. We get a small animation with this example. That's input for 12 values. So the bubble sort will do something like this. Every time they compare pairs, if this one is actually out of order, it's not. So actually we keep it. Otherwise, put the second one, it's out of order. We put the smaller one before, so we swap them. So we put 1 here and move 21 to the, swap those two. So 21, 1, and then we swap to 121, and then we compare 21 to the next one, 25, and it's actually in order, so that's fine. So we compare next one, 25 to 12, so it's out of order. We put 12 in front, so we can move 25 to the back, and you may find that 25 is actually the largest value in this input, so 25 will be pushed back to the end. So that how do we run or pass over the bubble sort. And then we start from the very beginning. Again, to the 18th, not 25. To the second last element, because the 25, the last one actually is the largest value. So we don't need to worry. After the second round, we're getting 21 is here. Second, we get 19, 18. So we do the bubble sort like this. And until we get around here, and you will find 1, 3, 5, 6, 8, 10 is actually in order already. If we still do the bubble sort, you just do more calculation, basically comparison, but you do not swap because they are in order already. Okay, now that's the total number of the comparations we do for bubble sort. So this one looks a little bit lower. That's the number we get for selection sort. So that's bubble sort. Okay, now we get the same question. For this time, we still get the pseudocode for bubble sort. And if you look at it, you will find, okay, still there are 2 loop statements. It's nested. So I get the same answer. So what is the input size, please? 5. You know it, right? So n, right? Okay, I really want to know whether you are still with me. So it is n? Thank you. So it is n. So the input size is a really important concept, but it's not difficult at all. I will keep repeating several times. I'm pretty sure you all know it. I will not mention this one again. So that's input size. And then again, for basic operation, so what is the basic operation here? Yes, it's comparison. We get assignment with addition. That's all the comparations. And now, final one. Can you summarize the number of runs, so the number of operations, the number of time to run the basic operation? Can you put it within the summation something? Yeah. Perfect answer. That's the one. Exactly the same one. Okay, now the one I want to mention here is you may find that this version is pretty similar like the one we did before. Can you raise your hand, please? Great. So what I want to show here actually is something like that. When we do actually the analysis of all those algorithms, you will find lots of the knowledge actually is quite similar to each other. So as long as you can grab all this knowledge, and later for the analysis, it will be useful. It will be useful. So that's the way you can analyze for nested operations. Right now we get is 2 nested for loops. If you get 3, I'm pretty sure you can do it. And more importantly, you need to know how to define for the index, the start index and end index. Now I will move on, and we get the same summation. We simplify, and finally we get this one is still the answer. Again, I will not talk the details of how do we do the simplification, but if you really want to know and you cannot work out, and come to the consultation time and just find me there, I will show you. So that is for Cn. And from here, we may find this one is exactly the same one we get for selection sort. So they get the same order of the complexity, but when we check about the best case, worst case, average case, they are different. For bubble sort, it's insensitive to the input, but for bubble sort, it is sensitive to the input. So which means if you give different input, you get a best case if the original file is already sorted. So we get about n squared over 2 comparisons, but we do not do any exchange because it is in order already. Otherwise, you get a worst case is actually sorted in an inverse order. So you do a same number of those comparisons, but for exchange, you still need to do all the exchange because it's inverse order. And then for average case, it's something like we maintain the same number of those comparisons, but for exchange, it's less than the max number. So that is the best case, worst case, and average case. Is bubble sort stable? Quick.
Yes, because you're never putting something way over the left side all the way to the right side. Usually it's only like while for my bubble group of 5, those 5 will never move into relative to one another.
Perfect. Yes, correct. Sorry, my bad. So perfectly right, because when you're sorting by using bubble sort, what you do is actually always swap. You always swap from the left side to the right side. If you actually is smaller, but actually if they get same value, you will never touch it. So that's the trick. So it is stable. Now we continue. So we will get to okay. Now, if we go back to check this one, you will find okay. Let me show you this one again. Now, after we do a number of runs, pass to do the bubble sort, and you will find for some part of those array, it's actually sorted already, even you actually did not do the sort for them. But this one is what we call the early termination condition for bubble sort, a very special version. And if you attended this week's prac already, you find that there are 2 bubble sort algorithms. Bubble sort 1, bubble sort 2. One is the normal bubble sort. Second one is bubble sort with early termination condition. So I highly suggest you go back to check the code if you did not do that to find where is that early termination condition. Now let's look at the theoretical part. Okay, now it's something like that. So we try to remove all those redundant iterations because if the previous part, if after one pass there's nothing changed, there's no exchange, which means the count value in there is in order already. So there's no need to do the further pass. So we just stop right there. That is the basic idea for bubble sort. Okay, why does this works? It's something like that. So now we do the analysis for best case, worst case, average case again. So now we are doing algorithm analysis. Whenever we do analysis, we will think, okay, we count the number of operations for the basic, so we count the number of basic operations. After that, we think whether that one is sensitive to the input or not. If it is, whether there is a best case, worst case, average case. So that's the whole story. I hope you can get this idea and put in your assignment. Put in your assignment, that's the way. So when we do analysis, normally we will talk, okay, is that best case or worst case, average case? So that's the one. Okay, now let's look at the early termination condition. So the best case will be the original file actually is insorted. So we only do one pass and n-1 comparison and no exchange. It's pretty quick. It's a huge improvement than the one from O(n squared). From here we get is O(n). So this one is linear, that one is quadratic. So it's a huge improvement for best case. For worst case, there's no improvement. For average case, there's one improvement. For example, the number of passes can actually be less than n-1. And the cost will be lower. So that is the way we do analysis for those sorting algorithms. You can change it based on some of the conditions. That's for bubble sort. Okay, now we get something more like computational geometries, something like that. This one is something like, I'm pretty sure you know something like this. I'm pretty sure you play some games like this. So now I get a question for you. So what if you get the game not working when you meet one mushroom, try to grab it, but it did not get that power for a new weapon or get bigger? If the game want to want to detect whether you touch that mushroom or not, what they call there actually is called collation detection. They will detect whether the people you control can actually touch the object you saw on the screen. Within there, what we do is we call the game collations. We will need to detect it. To detect it, you can have different ways to describe your people. You can use the square to detect, but square is possibly too big. But if you get several points on the peaks around the people, and you get a better description of your of the game. So from here, what we can get is when we do something like that, the algorithm behind it is something related to what we're doing. So what you need to do is you need to detect whether two objects really get conflicted to each other or not. So now we get one of the video to show you. It's pretty quick. So but from here, hopefully we can get some ideas. So you will say, okay, now we'll change a different rule. And every time we touch one of the objects, it will actually detect it. We detect it, there's one object, there's another diamond, we'll get different ones, they will touch it and find a way to go out. So that is the way we say, you need to detect it. Now, to our algorithm will be, okay, we don't care actually who you are controlling at the moment. What we try to get is how to actually detect whether two objects touch each other or not. So that one is we do need to get something like this. That's what we call the convex hull. So that will be something like, if we assume this dot represents one people or one object, how do you detect the boundary for this object? The way will be something like this. I'm pretty sure we can do that quickly, but can you invent one algorithm to detect the boundary for all those or arbitrary shape of those objects? That's a different story. Okay, the way we are going to talk today is we need to first understand what we call is the convex hull, something like that. So that's it. So the basic way is we want to find the smallest polygon that actually contain all the points. So basically that polygon contains all the points to describe one object. From here we get, that's the whole set of data points, and you get the right one, link them together to get the convex hull. And this one includes all those data points within this range. So that's what we call, okay, the convex hull. So to detect the collisions, the detection for the convex hull is actually that algorithm we need to do. But how can we do that? Good question. Now, to do that, using what we talked today is we use brute force. So easy. So what we do is we do something like that. We will try all the line segments, all those pairs of points, to say whether it is one boundary or part of the convex hull. So what does that mean? So we start from any point. We make this one pair to the rest of them to say if this one linked to this line, they get a line, they make sure all the other node is on one side of this line, and we say this one is a part of the whole. And we do that for all those possible combinations. From there, you will find this one is also part of the whole, this one is not. You do all of that. Finally, you can find all those boundaries, right? So now let's consider about the complexity of this algorithm. We first need to find all those pairs of combinations. We get n is the input. So how many of those combinations or possible combinations in there? The basically is n squared. It's n squared. It depends on whether you want to get the direction in there or not, you get different values. But if we're talking about the equivalent classes, so it's all n squared pairs of points we need to compare. And for each of those pairs, and we need to check the rest of the node is on one side or not, on one side of this line or not. So basically, you need to go through another n remaining points. So something like that. So we start from here, we get a comparison, we get n, we pick up another node, I get another n minus 1. So you will get n squared pairs of those possible combination of pairs. And then for each of the pair, you get a line. You will check the rest of the data points is on one side of that line or not. So you get 2 steps. First step, number of comparisons. Second one is you get the rest remaining points. You need to check whether they are on the one side of that line or not. So you get 2 steps, and the final algorithm is actually O(n) cubic. It's pretty high. I assure you, all the game we play right now do not using this algorithm because it's too expensive. Can you invent a new one? We are going to learn more, but the way we show today for this one is we only consider what is the brute force. And this example is showing you, for given one problem, using brute force, how do you solve it? So that as long as you get something like this, that's okay. And then we got exhaustive search. I think you got a 10 minutes break. And then we'll come back.
Yes, so it's not the index.
No, it's not index, it's the instance. So what do we call it, for example, I think go back to so which means we get a two row times market set. So the row was a value for that element, and the 2 will be the number of instances. Because it's multi-site, we can get rid of just have how many those instances for one element. So that's multi-site.
Okay, got it. And of course, another issue that so like in can I just add another file like for Java, and then like I create a new file called the node.java, and then share the okay. So like I share all the node between no. Like I share the same node for all the links here. Okay, got it. Or I can share. Yes, second.
Okay. Okay, cool. Settle down, please. So let's get back. So after we finish the lecture, I will go through the assignment. So I suggest to go to the end of the lecture because I will show you for the assignment if you feel that's too much and how do you actually break the assignment into different steps. And if for each of the steps, actually we covered in different lectures and labs, and you can get immediate help from there. So now let's continue to what do we get for the lecture. So now we get exhaustive search. So exhaustive search is something like that. So we do the sorting and we do the searching. And here is we do, for some of the problem, we do need to using exhaustive search. So that means we basically need to enumerating and generating all the possible solutions and select the best one. Now, I know this one it's easy for us to understand, but let me link this one to what we talk in today's lecture. So remember today we talk brute force. So that actually is brute force for search. For what we do is, brute force means you try all those possible solutions, find the best one. Same thing like this. So we want to do search, so we generate or we enumerate all the possible solutions. The difference is will be something like that. When we're talking about enumerate, is basically go back to something we call within mathematics. So you enumerate something in a systematic way. So in case you do not ignore any of those possible solutions. So which means you need to get a full set of all those possible solutions and then find the best from there. So that is brute force for search. Just like what we did for selection sort. You go through all those possible solutions, and then you go back to get the order. And here what we get is we try to set. What we set here is something like that. We want to find all the potential solutions to the problem in a systematic way, and then we want to get the solution evaluated one by one and finally find the best. For some of the cases, you will have to use some brute force strategy to do it. And one classical problem is this. We got knapsack problem. So basically, what you get is you get a knapsack, it's a bag. Basically, you get a bag. The bag have a capacity, and you get a list of atoms. For each of the atoms, they have a different weight, and have different values. So what you try to do is you find the most valuable subset of all these atoms, and it can be fitted into the bag. So that is the problem. Now, how to do that? We can use a brute force strategy. We enumerate all those possible subset of all these atoms, and then we enumerate all of them, and then we select the best answer. So that will be the way we do. So that is a brute force. Okay, now what we do is we consider all the subsets of the set of the n atoms, and compute the total weight of each of the subset, and then we find the subset with largest value among them. So we get this one, and the complexity for this one will be 2 to the power of n, because you get the input set is n, and you want to find all those possible combination of those subset. So that will be n to the power of n. Each of the atoms may possibly be selected, so get 2 to the power of n. And then, so the complexity for this algorithm is n to the power of n. So this one is exponential. It's very expensive. It's very expensive, but sometimes it is necessary. Now let's get back to our problem. So the problem here is we use the idea of brute force. Now we try how do we do it. Here's our bag, and the capacity is 10, and we got 4 atoms. Each of the atoms get a different weight. 7, 3, 4, 5. You get different values. $42, $12, $40, $25, different values. And when we do the brute force, what we do is actually we generate all those possible subsets. Nothing selected, all selected. 1, 2, 3, 4. 1, 2, 1, 3, 1, 4. That's all the possible combinations. This one is 2 to the power of 4. We get 4 atoms, right? And then we calculate the weight for this. And for the weight over 10, we saw that's not possible because our bag get a capacity is 10. So any of the combination get the total weight is over 10. We saw that's not possible. And then check the rest solution, find the largest value we can get. It's 65. Now we get it. So that is brute force idea for exhaustive search. Okay, now we get something more useful like a graph search. Graph search is really quite useful. I'm pretty sure you use it every day, as long as you use any of the smartphone. It's actually graph search. For example, you want to get location from A to B. You need to search. And normally what we do is we will represent all these road and intersections, the road as lines, or we call edge within the graph. The node is the intersection, and we get that as a big graph. So you can search how is that the shortest path from A to B. And then you go to the maze. It's also one way you need to search. And what you represent this maze also represent each of the intersection and each of the lengths at those graphs. You can search one way out from A to B. And here is actually, you can check the graph search check whether one network is connected or not. You can check the connectability of one graph, connected graphs. So that's the usage for all those graphs. Now, if this one is too big, let's get something pretty easy to understand. So something like this. Let's imagine this small graph is a graph represented for a location, like Melbourne. And each of the node is the intersection. Each of the link, we call edge, from A to B is the road link from A to B. And sometimes you may get lost, if especially go to a new city. If you went to Hong Kong, it's quite easy to get lost. So that's why I get a T-shirt to print something like I'm lost in Hong Kong. So that case will be okay. If you get lost with a new place, you want to find somewhere. Like I want to go, if I'm at A, and I want to go to my hotel and F, I don't know where actually is F. I will try all the possible street I can get at the moment when I'm standing at A. I'll get a different way I can try. The first way is I will try something like this. I will go from A to B, and I will find, okay, whether this one is correct or not. I will pick up the second one, not the one, go back to A, go to the next node linked to B, either to B or to E. And the second I want to go. If I'm lucky, from A to B to C and to F, I will get it. So that's one strategy. So this one seems something we call the depth first. Another different strategy is I'll try something like this. I'll get from A, go to B first. It's not correct, go back to A. And select C. C is not correct, okay, go back to A again. And go to next neighbor for A, so I get D. So this one is called a breadth first search. So that's on graphs. Okay, now let's explain why we do this. Remember what we do right now is we want to do search on the graph based on brute force idea. So which means we want to search through the graph to connect each of those possible nodes. Like if you want to delivering somewhere, each of the node is the destination. There's no chance you can escape. You have to go there to deliver something. So which means you don't need to search a way to make sure you access each of the nodes. Now, we are going to talk two ways. We talk the depth first search. So depth first search is we first choose an arbitrary node, vertex, and then mark it as visited. Okay, it's something like that. If you know where you start, like I lost in Hong Kong, I know where I am. I start in the point, I start from here, do a depth first search. That's a different way. You will search from A to a hotel. And this one means, okay, you can start from any arbitrary vertex within the graph. The purpose for this one is to check the connectability of the whole graph, to make sure your search will search all those nodes within the graph. So that is what we get this algorithm. So we choose an arbitrary vertex and then mark it as visited. And then the point here is from the next move, what you do actually is you proceed to the unvisited but adjacent vertex and make it visited from A to B. And after that, you repeat this step. Every time you will actually pick up an unvisited adjacent vertex of your current node. So that is depth first. I go from A to B. I was standing at B and look at all those unvisited adjacent neighbor nodes. Starting from here, pick one and go next. So it seems I go down to somewhere, down, down, down. So that's depth. The depth first search. And then at each of the dead end, which means when you go to one node, all the neighbors are all marked as visited, or there's no neighbors, so you backtrack to the previous node and find the second neighbor in there not visited, and it goes that way. And finally, the algorithm will go through all those nodes within the graph. Now we get one example to show you. Remember, I'm at A, and this time I'm not going to find my hotel at F. What I'm going to do is I want to start from A and visit all those nodes within this small graph. I will use the depth first search. So I'll first get A. I'll go to B first. So depth to the first one, and then I will start from B, go to another unvisited neighbors for B, that will be C or E. C, so we get C, and then we get C from the neighbors like A, say F, A is visited, D is not. So we go to A is visited, we go to D. Go to D, and then we check all the neighbors for D. We get A, F, and C is that one we just visited. So we check A is visited, so we go back to check the next bit for F is not visited. So we move from D to F. Okay, now we notice, we check about C, we found C is visited. Okay, then what we do is we move back to D, and we find all D's neighbor also visited. We'll go back to C again, and then we start try C's next neighbor is not visited, that will be E. And then we go back to E, visited. We select the one we try is all visited. Now we back to C, back to B, back to A, all done. So that actually is the depth first search. Okay, now why we do this? Because sometimes, as we said, you will have to go through each of the nodes. In that case, you need to use the brute force idea to make sure you do not actually miss any of the node. So in there, you want to enumerate the paths in a systematic way. You can either do depth first, or you do the breadth first. So now we do the depth first, and we check the pseudocode within here. And for this pseudocode, I will not give the question like what are the input size, what is the basic operation, and what actually is the big C, the number of those iterations you run on those basic operations. But I will give the answer here. I hope you can work it out at home. I will show you the answer later. Initially, when we discuss this one, we put it as a kind of a homework, so you can do at home. But later, we think it's good we show the example and briefly go through what is the solution on lecture, and go back home, you visit it again. So it's something like that. Now, let's look at what is the DSF. So the depth first search. So we go through all this. We found, okay, that's the initialization. Mark all the nodes unvisited. And we start from the first node to the end node. That's all the node. We find whether this node is visited or not. If it is not, and we will do depth first search recursive, second algorithm. And from this one, we call it self. And from here, you will find this one looks a little bit more complicated. Yes, it is true. Because within here, we get this for loop, and this for loop get one of those recursive one. But we discussed the for loop already. We even discussed the nested for loop. And for recursive relationship algorithm analysis, we analyzed last week, right? So I would like you to go back home and if you're interested in, try to work it out. How can you get the big CN for this depth first search? Okay, now I will directly give you the answer. And from here, I get two things. Remember, we discussed about the implementation for your data structure, for your abstract data types. For example, here we talk about graphs. And the graphs can be represented in two ways. One is matrix, another one is use the list. And if you use two different ways to do the implementation, and you will get a different efficiency, basically complexity. So little to big O are different functions. Okay, now I get a lot of text here. I will explain. So something like that. So when we do the matrix representation for the graph, we want to check the connectivity for each of the nodes. So basically, we will need to go through all the nodes, right? For each of the nodes within the matrix, represented as a row. And when we go through each of the nodes, we need to check all those possible nodes recorded within that row. So that's the connectivity to the rest of the n-1 node, right? So you basically need to get n multiply n checks about the connectivity of the node. So that is why we get n here, I mean, is actually the size of the vertex site is the number of the node. So that's v square. So that's it. So that's the basic idea we get. And then if we go to use the linked list, you will get something different. For linked list, we get all those nodes. And for each node, they get a linked list to list all those nodes connected to this node. So the worst case will be something like that. For each node, you need to check all those connected neighbors, and each of the connected neighbors may be different from one node to another, but one thing not changed is the number of edges within that graph does not change. If you map the number of edges from the graph to the linked list, you will find the number of edges with the graph equal to the number of links you put within this linked list. Because when you represent one node A to B, you get a link from A to B. That's basically one edge. That is what we get about E here. That's the edge. So you need to go through all the edge to make sure you check the connectability for all those nodes. So that you get V OE. And V actually here is actually something like you set up the visitor status. It's required for OV complexity. So while we put those two terms there, it depends on the sparsity of the graph. If you get more node than your edge, and then the first term will dominate the efficiency. If you get a complete graph, and you get a smaller number of V, and you get the E is quite big than V, and then you possibly can discuss the first one. So it really depends. When you do analysis, possibly we put those two together. But again, don't worry. For this kind of equation analysis, it's not done by myself. It's done actually by all those scientists within this area. I have been researching this one for decades, so they get some very concrete analysis about the algorithm. So when you really go to a new algorithm, there's no one can expect you will give some solid result like this at the very beginning. So don't worry. So we are at the university, so we teach. We learn some classical ways, and we talk the best. But to start from here to the best, there's a long pathway. That's we all know. So don't worry. As long as you can understand, great. So basically, within the final examination, I will never put one algorithm to say, now here's one algorithm, here's the pseudocode, work out the efficiency like this. No, I will not do that. So that was I try to say. So the point is you need to understand. Now we go to the next one. The next one is we'll get the breadth first search. So from here, what we do is we get a different strategy. We now go to we start A, we check the neighbors, but we don't go there. We check the neighbors, and then we stay here and check the next neighbor of the counter node. We now go to the next neighbor, and go to the next neighbor again. So we stay with it here, check my first neighbor connected or not, and check the second neighbor, third neighbor, make sure I do a complete check at the counter node, and then I move. So that is what we get a different strategy called breadth first search. So the point here is you start from an arbitrary vertex, and each time you visit and mark each of those adjacent vertices for the count node, and then you move. So that will be the way that will be the difference between those two searching ways on the graph. That's two very classical ways. Okay, now we get one example first. So we start from A again. So now we do not do depth first, we do breadth first. So we get enough A to B first, and then to C, then to D, and then we get B. Check C is connected, then check E, and then we check C. So we check A's neighbor first and neighbor B, and when B's neighbor all checked, we go back to check A's next neighbor C. C connected to D first, is checked, and they go to E checked, go to F checked, and they go back to check D, and D's neighbor F is actually also visited, so that's all marked. So that is two different ways about how do you search all those nodes on the graph. Okay, now finally we get the complexity for the DFS and the BFS, and that is the applications. Okay, now here's the point. Here's the point. So after we understand two different strategies you can search on a graph, and for each one of them, they get different applications. For example, if you want to find the shortest path, it's quite useful. You go to Google Maps, you search from the destination, from here to your home, you will find the shortest path. Normally, that's the way they give you. They may put a different weight on it, but that's what they call the shortest path. To do that, they will use the breast first search. The breast first search is the one they do. They may get a different version, but the original version is something like that. So that's the classical way they do. And the interesting thing is actually when you check the complexity for those two different searching algorithms, they are actually the same. Why? Because the whole problem is to get a graph. You want to do a brute force search for each of the nodes, get it connected. So, which means there's no shortcut. You will have to visit each one of them so you get roughly the similar level of complexity. So that's it. But in reality, they are different. So that's what we are going to talk next. So we get summaries for today. So it's not the end of the lecture. Remember, we still get something else to talk. So I just summarized the brute force. We talk the brute force for sorting, for computational geometry, and for search, and for graph search. Now, let me quickly go through to assignment first, and then we go back to what we left within last week's lecture. Okay, now for assignment. The first one is for the deadline. So the deadline is actually the 27th of August to the midnight. Okay, now what I want to say here is I understand my rule. My rule here is try to help. So do not get too much pressure about the deadline. If to the end of the deadline we found 30% of the students did not finish the assignment and you put in a request, I can extend it. No problem at all. But all I want you to do is do it by yourself. I will mention later. So for the deadline, try your best. If we do really need to extend it, I will extend it. I will do that based on the request I get from all of you. If I only get 1 or 2, possibly not. If I get 20% or 30%, I will do that. So do not get too much pressure about the deadline, but please make sure you work on it and try your best. That's for the deadline. The weight is the 15%, and for pairs of assignment, I get some requests from your peers and want to work on the assignment individually. For me, that's okay. But what I really want to highlight here is, especially for programmers, later when you go to when you go to industry, there's no way you can do one job by your own. I can tell you right now. All the time you have to get a pairs or you get a team to work on it. Sometimes, most of the case, you get a team actually is just constructed for a very special project. You really don't know your partners, but you will have to get the project done. So what I try to say is, please, if that's possible, get a partner and work with them. Try to manage the relationship with your partner, get one job done. It's one ability you need to have. Okay, one thing I add here is I promised you I will get my colleague at SICK to give a lecture or give a talk about how this course can help the guys within SICK sitting over there around the SICK. That's the high office in there. I will get him in within 2 weeks. I will give you more details later. But from either you'll get a better understanding about why this course is something like that. So it's all teamwork. There's no project you've done by your own. So if possible, please try to get a partner. It is important. Okay, now we get something like this. We get 2 tasks within there in assignment A. So the first task is you need to do implementation for multi-set with different data structures. So please keep quiet because we get hundreds of people here. If you keep talking, the rest of the students cannot hear. So please keep quiet. Thank you. So we get 3 different implementations, the doubly linked list, and the sorted doubly linked list, and the binary search tree. So what I try to highlight here is something like this. Double linked list actually is what we demonstrated within lab 1. And for sorted is what we talk within lab 2 and 3. So you get a different sorting algorithms. So what I expect you to do is put that sorting algorithm out and put on your double linked list. So that's it. So you get a sorted double linked list. How to do it? That's your assignment. The third one is for binary search tree. It's in lab 4. I did not list the lecture. I just put in the lab because for the lecture, I will not talk to you how to do that in implementation. I just talk something like the theory, the pseudocode. But when you go to the lab, you will definitely see the Java implementation. And if you get stuck, raise your hand. I'm pretty sure your lab demonstrator will approach you and help you to solve the problem. So please make sure you understand all these labs pretty well, and then you get half your assignment done. It's task A. That's what I emphasized from the very beginning of the course. Please make sure you attend the lecture, the tutorial, and the lab. They all work together. The lab is directly related with your assignment. So that's for the 3 links. And I put something in here I don't want to mention too much. I do need to mention, but I do need to mention. So in each year, we do find some of the students copy or use some of the existing library online. Please don't do that. So you do need to implement your own this linked list. There are some libraries. Some is actually quite well known. Some actually is just released by somebody else. Don't use it. Please do your own implementation. If we find some people use it, sorry, you will get 0 marks for that part. So please make sure you do not use it. You need to implement your own node, your own method, your own linked list and a binary search tree. Do not get existing list. You mean for the assignment? Yeah. Okay. That one is for demonstration purpose to show you when you run the code, what kind of output you will get. It's not for demonstration how do you do the assignment. A good question. I will give you one chocolate. The question is really good. The question is, sorry. The question is, when you check the source code provided for assignment 1, and there are 2 more functions implemented already, and when you check there, we did not implement that by ourselves. Because, we have to spend an extra hour to do that, and there's no way I will test myself. I cannot mark myself, right? So what we discussed is we just use the existing set. We focus on how to check the running of the code, the input, output. So that's it. So you don't need to follow this one. Do not using existing libraries. Any question about this one? Cool. So we continue. So now we get task B. So task B is evaluate your data structure. You need to generate the code. You need to generate the data. We get a data generator actually within this week's. It's lab 2. We get a data generator there. But the difference is you need to pay attention to the value, the type of the values. The data generator we put within the lab actually is integers. But the data type we use within assignment is not. It's a string. If you read the assignment specification, so that's why you need to change.
How many input we need to put, like 50,000 or like 10,000?
Good question. That's what I'm going to talk next. Sorry. Don't worry, how come? So don't worry at all, I got my job done. Okay, now let's continue. That's a good question. The question is when you test it, so what is the size of the data you need to get in there? So that's what we get, something like that. So it will be evaluated. How to evaluate? Within here, there are 2 ways to evaluate, theoretically or empirically. And within lab 2, we discuss several ways you can use the nano time. You can use the timer command within Linux to time it. So that's the way you can do. You can do either way, both. That will be great. And then we check the assignment specifications. You will start, it will be actually evaluated in terms of the other time complexities for different operations, add, remove, or search. And for the size of the multiset, please go back to check the recording. When I go to analyze some of the algorithms, they have different actions, and they have different efficiency if they get affected by those different actions. and within your assignment, especially for the second one, evaluation, in report, I hope you can get something like that. I'm pretty sure if you get it done in a perfect way, professional way, and you can use it to put it in your resume later when you find a job at SICK. It's quite useful. Yeah. And then we get different sizes of the scenarios. Let's go back to your problem. So you do need to use the different size of a multi-set. Okay, now, what is the differences? I'm going to show you about later when we go back to the lecture we left within last week. Let me quickly go through this one. Finally, you get 6 pages for our report, and the report structure and the marking guide is actually included within your assignment specification. Please make sure you go through that one. 6 pages max. And the font size is 12. That's your report. What is expected is within here. Analysis. Okay, now for the checkpoint. Initially, we put in the checkpoint within week 4. That actually is next week. But we get feedback from this week's lab attendance. So said, okay, for double linked list, some of you have not studied, and some of you have not found your partners. So we put that back to the week after. So the checkpoint for the 2 marks for the implementation of the linked list is within week 5. The lab is not a week 4. It's the week after, not next week. So you get some more time to do the implementation for linked list and for to find a partner. That's what we get. And finally, for report. Okay, now, any more questions about assignment? So you mean how to generate the data you try to insert or something? The size of it?
Yeah, like showing as a unit test or something else.
Okay, let me go to here. So that is what we are going to cover within last week, what we left with the empirical analysis. Thank you. You always get what I'm going to talk next. That is great. So that means you are still with me. Come on. Sorry. Okay, now let's continue to what we get about empirical analysis. This one is directly useful for assignment 1. Now we get something else. Before I go through all these ones, I will look at this one first. I like it. It's something like in theory and practice should be the same, but actually they are not. It's the one we get from Albert Einstein. So it is right. So that means something like that. For theoretical analysis, what really we can get from there is we can do analysis without implementations. We can discuss that within extreme cases. But do remember, when we do the theoretical analysis, we ignore something. We ignore the constant. We ignore the lower order terms. We ignore those coefficients. But in fact, in practice, those terms does matter. So that's what makes the difference between theory analysis and practical analysis. That one does not mean, so do not translate this one wrong. The wrong translation about this one is theory is useless because they are different from practice. It's not right. It's just they are different because the theory can help you to analyze some of those extreme cases, something like the upper bound, lower bound, and exact bound. But for practice, we will have to consider those constant, coefficient, low order terms. So that's the difference. As long as you understand, we can see the difference from here. Okay, now we get the empirical analysis. So this one basically means that we estimate the running time. So to do that, we need to measure the actual time implementation task. So this one is really important, especially when you get 2 algorithms have the same order of the equivalent class in terms of efficiency or complexity. In that case, theoretically, there's no difference, but actually when you check it, you will see the difference. Especially when you check it across different cases, worst case, best case, random cases, or average cases. Or especially when you check for different actions, insert, removal, or you do search, you get a different performance. Because when we actually do the analysis, we said, okay, whether you compare, whether you go to assignment, whether you go to addition, we think that's roughly the same basic operation. this will tell you in practice they are different, so that's the way you need to measure. So the combination of theory and practice will make you a better programmer and a problem solver. Now we continue. So we normally do the assignment something like that. Okay, so that's the way you design for practical experiments. This one is especially useful for your assignment at the moment. That's why I put this one down here after we talk about the assignment. So you can do, say, understand the experiment's purpose. So for your assignment, what do you need to do? And then decide the efficiency metric. It's actually you want to measure the nanoseconds, or decide the characters of the input samples, go back to your problem, so that will be the size of the input. You want to do 1,000 of the insert, 200 of the removal, and 300 of the search. So that's for different characters of the samples. And prepare the algorithm, prepare the program implementation. So we get it already. So you need to get a 3 implementation, right? And then we create a sample input. Okay, that's the sample generator. And then run the algorithm on the sample's input and record the data observed. Please make sure you do this one on the core teaching server for your assignment. But for your own job, please do not do that. And then we analyze the data obtained. That's the report. That's the perfect order for your assignment. Now you can follow this one to finish your assignment. And actually, that's the same order we use in real project. It's all the same, just a different scale. For assignment, a bit easier, a bit small, to make sure you can finish it within 4 weeks' time. And for real project, it's not like that. But they all follow the similar procedures. So now let's get 2 things. So for practical performance of those algorithms, 2 things are important: the input and the algorithm. The algorithm means for the same problem, you get a different algorithm to solve it. We get 2 sorting algorithms, merge sort and quick sort. For what actually is merge sort and quick sort, don't worry, it's just 2 sorting algorithms, like selection sort and bubble sort. So what do we get those 2 is, we'll cover those 2 algorithms later. What I want to highlight here is, for the similar algorithm to finish the similar job, they have very different performance. Something like that. We check the running times. For merge sort, quick sort, and selection sort is what we discussed today, is actually a brute force. So this one is clearly taking more time. So that's it. That's what we get on randomized list. It seems all correct. Quick sort is pretty quick, then merge sort, then selection sort. But when you change to order the list, you get a very different result. Right now, we can find, okay, merge sort is pretty quick, and for quick sort, it's not that quick, actually. For selection sort, it's not that bad. On these extreme cases, and for your assignment, I hope you can find something like this. You test for different angles, for different input size, for different operations, different sort of input. So that is ordered list. Now, the input size also affects the performance. So what this one means is something like that. We get 2 search, linear search and binary search. In theory, the linear search you get O(n) is the complexity. For binary search, you get O log n. So this one is quicker. Binary search. Linear search basically is sequential search, something like that. And when you check these 2 relationships, the x is the size of the input, y is the practical time run in seconds. And you will find, okay, from here it seems no big differences. Sometimes linear is better, sometimes binary is better. But what theory can help you is when you increase the size of n. When we increase the size of n from 0 to 1 million, you will see the difference. But when you increase the size from 0 to 1,000, it's not big enough. So 1,000 is not that big. So one example is, let's talking about the web. Currently, the website or the web page, there are billions, even more than that. So when we're talking about the calculation on that level, theoretical thing does help. So that's why we say, okay, the theoretical one and the practical measurement may be different, but you need to notice what is the differences. And hopefully you can find something from your assignment. Okay, now that will be all we get for today. I hope this one can give you some indication for assignment. If you get any questions, just let me know. Thank you. Hello. Yep.
With the once we do implement,
Yep.
we do testing on the
Cross it again.
testing on for the user.
Yeah. Okay. Marking. Because when we do marking for over 300 students, and if you own compile on your own machine, and we cannot really get it. So we have to see we all get it compiled somewhere, make sure it's reliable. When we mark it, it can be run. That's no. Okay. Yeah. The Linux solutions have different versions, different compilers, different versions for Java. So make sure you do that in testing phase. Cool. Thank you. Yeah.
So I just wanted to ask so I have Java, like the JUnit test for so should I have some kind of test like a JUnit like I write a single unit test for our assignment. Yeah. So we just use the Python.
Yes. The Python code is the one provided, and marking will use the Python. So the Python code will run into your Python code will run somewhere to standard input. Standard input to get into the output, code input, and just really the output is the one with if there's anything wrong, you get something wrong, you will not get marks. Yeah. So please use the Python code to do that test yourself.
So then how should we generate the data as you said?
Just data generator. That's your assignment.
So we just find some strings or whatever.
Yes. You can, from anywhere you can find those strings. And how do you get this data generator? You can go to this loops. There's a data generator for integers. Similar idea can be used. But you need to work out how to change from integer to string. Yeah.
इसके साथ तो अलग है कोई ग्रेड है फॉर एग्जांपल स्ट्रिंग अगर नहीं होता तो कर लेंगे ठीक है देख लेते हैं if I want to generate 1000 string different randomly do I need to generate string with 8 characters getting the point
So do you mean you want to check with the verses?
no if I want to generate 1000 strings so do I need to generate them with a fixed length
Oh no, you don't need to. It should be random. It should be random.
3, 4, 5, 6, 7, 8, 9, 10, whatever.
Do not make 100. That's impossible.
Impossible. Up to 10, 15.
Yeah.
And the second thing is, you have already provided skeleton code, you know? So we can use that code in our assignment, yeah?
Yes.
But not the libraries.
You have to use it.
We have to. Maybe I missed the point, that is why I
No,
thought
we use
get the
specification. We get several files. Some of files we said, okay, you
You don't need to modify them.
and do not modify. Do not modify, keep it here. For the one you need to implement it.
Implement.
Yeah, that's very easy.
Thank you so much.
Cool. Thank you.
मैं बाहर ही कर रहा हूँ
That's why it's not really a job.
Yeah, I know, because the one I had me
Yeah.
to struggle closely is on.
I would suggest try to get a partner. If you really cannot, I'm happy for you to work on your own if you want.
Okay, yeah, so no to three.
No, sorry.
Okay.
Okay, please.
Thanks.
Thank you.
Yeah, how can you register the group?
Sorry, say again.
We need to register the partner in any of
That one.
So you mean how do you show you are group?
Yeah.
We do the summation.
Okay.
So when you do the summation, there's a one top. I think within the summation specification within assignment 1, there's a one thing you need to provide. What are the partners? If you're single people or both of two, you get your you got file to say you are two, and you put your student ID within summation code.
Yes.
So both of us need to upload the assignment or only one?
Only one.
Okay.
Only one. So we will release how to submit the details later. Yeah. Cool. Okay.
I was wondering if we were allowed to use different languages in the assignment.
That's a hard one.
And
So what language are you trying to use?
I wanted to use C because I haven't got an up-to-date version of Java on my laptop.
Okay. So what are you trying to use? Sorry, I didn't catch
C.
C. See, okay. Okay. Another question related to this one is: did you attend the lab? Can you get it? Because the lab all in Java. You happy with it?
Oh, right.
So is it?
I think I went home because I was tired after the last lecture. So.
Okay.
Can't you run Java on the Titan, Jupyter, Saturn servers that you're supposed to connect to?
You can run Java. So you can run Java. You can run C.
I mean, it has to be able to compile and run on those things anyway.
Yeah. The C compiler is in there. On the Titan server, they have C compiler. But the question is, we did not actually tested how to run the code to crash it in there. Personally, I'm fine. I'm fine for you to use C, but I do not really suggest.
Okay.
Yeah. If you really want to use it, that's okay. Let me know. Can you drop me one email to say you use C? I will pay attention to your submission.
Okay.
And can you also give another file? Explain how to compile a file on the core team server.
Oh, yeah, sure.
You get the details how to run your code basically, and make sure your code. Yeah. So drop me one email. I will give you more details to how to do that. Just make sure the marking will be easier.
Yep.
Yeah.
Sure.
Cool.
Okay, I'm still confused about this no use of libraries thing. So the assignment specification lists a bunch of the files that are in the source code provided.
Yeah.
Some of them it says don't change this.
Yes.
For others it says complete the implementation,
Yeah.
complete the bits that say implement me.
Yeah.
And those files have like classes that extend things from the Java utils library. And then they have a bunch of methods and things in them that say implement me. Yeah, this thing.
Yes, I know this one. Smaller. Okay, so which one? So when we say do not modify this file, so which means you do not need to change this file. And this one means there are some of the functions missing within here, and we label it as implement me. That's basically a function like insert or add or removal. You insert the function in term. So basically, what we did is we defined the interface already. We define the interface between different classes. How do you do that? So do not change the interface, and only do the implementation of the code.
But what's confusing me is that these files, they contain extends things from the Java utils library, unless I'm misunderstanding them, which we've been told not to do.
No.
Let me. So he's talking about the thing is said do not use the linked list. Said, and is you talking about this one?
Is that your
the linked list, is that what you said? Like you will get a 0 mark if you use the linked list of a Java, like a hash map.
Yes.
You can't.
So do not use existing libraries like the one within the.
But unless I'm misunderstanding how the provided code is written, it already does that.
Okay, let me. Okay, so you get confused about this hash master and the.
Okay, can we bring up the? Do you have the source code here?
Let me go to the web to get it. Should be easy.
Oh, actually.
We can use the what's in the lab. The solution. Can you use this one?
You can, but you cannot use it directly. You have to modify something. But
yeah, we need to modify, but we can take that idea from there.
Yes, sure.
So bring up, say, linked list multi-set.
This one?
Yeah.
Okay, at least you can see it.
All right, so you have here, you can see that in the class definition it has extends multi-set, which is from Java util.
No.
Isn't it?
No.
Oh, it's from,